thanks organizer for invitation. It's a real pleasure to present my work dedicated to Brillouin scattering in optical fibers. So I'm full-time researcher, CNRS researcher since 7 years now in Femto-ST Institute. I'm working on the optics department and with many collaboration with the Photonic department in the same institute. So today I will speak mostly on optical fibers and Brillouin scattering. So I will present you different fundamental aspects of Brillouin scattering in optical fibers and different applications of this Brillouin scattering. So to start, you know probably that the velocity of light is fast and the sound is slow. But in terms of wavelengths, it can be the same order. For example, in optics, with a wavelength of 1 micrometer and a velocity of 300,000 km per second, you have a frequency around 300 terahertz. And if you have acoustic phonon with a frequency around 2 gigahertz and a velocity of 500 meters per second, 5,000 meters per second, we have also wavelengths of 1 micrometer. So it's really interesting because if optical and elastic wavelengths can be on the same order in the micrometer range, despite the huge difference in frequency. So if you find different waveguides, so optical waveguide, you can also confine optical mode, but you can also confine and alter the acoustic wave. So different waveguides. So first, for example, the single mode fiber. So this is a macroscopic image of the single mode fiber. So it's a really standard silica fiber. I just point here the red circle for the doped core. So it's a germanium doped core. Another waveguide, which is really interesting for photon and photon interaction, it's a photonic crystal fibers. So here the light is guiding by the defect in these photonic crystals. So it exists many photonic shame. So you see here this shame here, another one here, another one, etc. And the last waveguide, it's called nanofiber. It's a very long tapered optical fiber. So we use this fiber, we taper, and we obtain a very long silica rod with a transverse diameter smaller than the optical wavelengths. So this is a three different waveguide for my presentation. So this is the outline. So I will briefly introduce optical fibers and Brillouin scattering in optical fibers. After, I will present you some fundamental aspects in a standard single mode fiber. So it's standard, it's telecom single mode fiber. So here it's a spool of 10 kilometers of standard fibers. The second part, it's dedicated to Brillouin scattering in photonic crystal fibers and how the hair hole microstructure modifies the light-sound interaction. And the last part will be dedicated to tapered single mode fibers. So in details, in standard single mode fiber, I decide to focus on really two opposite way. One, it's a fundamental limitation in telecommunication, so due to the Brillouin scattering, and another one, it's a distributed Brillouin sensing in long single mode fibers. For photonic crystal fiber, I've chosen two examples to see how the microstructure modifies the light-sound interaction. First, it's a forward Brillouin scattering, and another one, it's a description of a new model to explain the Brillouin scattering in this fiber. And finally, on tapered single mode fiber, I will show you some tapered chalcogenide fibers to reduce and enhance Brillouin scattering, and another one, silica fibers with new interaction and spectroscopy effect. So first, silica optical fibers, so very standard silica fibers. So you have the core here, the cladding, and the protection. So the core, it's doped to guide the light like this. So this is here the refractive index profile. So we have a total internal reflection. So the dimension of the core depends of what you want, single mode fiber, multi-mode, as you want. And here it's more standard, this 125 micrometers. It's really a constant because it's really important for a connection of different optical fibers. and this is here the mechanical protection. So it exists many optical fibers, but we can separate in two classes. One is monomode, five fibers, so with one fundamental optical mode, and another one is multimode five fiber with large core, and we can say different mode with different propagation. So we define a numerical aperture here, V parameter to define the monomode and multimode propagation. And historically, this guy, Charles Cao, he received the Nobel Prize 10 years ago for this measurement. He measures fiber losses as a function of wavelength. Because before Charles Cao work, we imagined that this OH absorption peak go to infinite, and it's impossible to measure the transmission after this wavelength. Charles Cao demonstrates that it exists a minimum at this wavelength, called now telecom wavelength, so 1.55 micrometer, where the losses can be done very low. So now we know that the losses, it's reduced to 0.2 dB per kilometers, so it's really low. Perfect for data transmission. So, and the limitation is not the waveguide imperfection, is not the absorption in mid-infrared or UV, it's Rayleigh scattering. Okay, Rayleigh scattering is the limitation of losses in optical fibers. So Charles Cao and his colleague demonstrate that photons in silica are better than electrons in coppers, but at this time the attenuation 1000 dB per kilometer, so impossible for data transmission. But some people working to reduce this attenuation, so it's mainly the problem of fabrication, etc. And he obtained 20 dB per kilometer, so it's quite nice to starting to working data transmission. And 30 years ago, Corning in USA produced a very famous fiber called SMF28. Maybe you know this fiber, with a very low losses, 0.23 dB per kilometer. So this fiber starts the data transmission, mostly for internet, etc., etc. So now today, the losses down to 0.18 around telecom wavelengths. So after 100 kilometers propagation, we detect 1% of the injected power, and it's enough for telecommunication because we have very high quality detectors. So it's not necessary to detect more power. So if you want to inject, to transmit data in longer span, we need optical amplification. So now about Brillouin, Léon Brillouin. So probably you know Léon Brillouin, and this paper published around 100 years ago. Yes. So diffusion de la lumière des rayons X par un corps transparent. So this is, you can download the paper now in this Annales de Physique. And it's, I really like this paper. You see, this is abstract. So sorry, it's in English. But he explains the diffusion of it's in French, so sorry. So he explains the diffusion of light. So when you inject a light in a homogeneous media, fluctuation of density linked to the great diffusion. And this last sentence is nice because he says this diffusion is probably very low. So it's not right. So sorry. So you know probably Brillouin scattering process. So this is the Stokes process. So just short resume here. So we have the optical wave here. So optical wave vector and frequency wave optical frequency. So you have a sound wave propagating like this with acoustic wave vector and frequency, and a small part of the light is scattered by this acoustic wave, so backscatter, and the optical wave vector is equal to pump wave vector minus acoustic wave vector, and the same for the frequency. And in anti-Stokes process, just the sound wave propagates in opposite direction. So the backscattering light is shifted because the sound wave propagates. It's a Doppler effect. So this is the Brillouin process. So you can also define the acoustic wave vector equals 2 times optical wave vector multiplied by sine theta over 2. So acoustic frequency is given by this relation. So depends of refractive index of the materials, the longitude, the acoustic velocity in the material, the pump wavelength also, and the angle between the two optical waves. So Léon Brillouin was a very famous scientist. You know, did you find where is it? No, it's here. So he participated, I think, in all Solvay conference. So it's a really important conference with, you know probably all, mainly of this scientists. This is interesting because the paper published by Brillouin is in French. And it's very difficult to write now in paper in French and to diffuse in a community. And I think Léon Brillouin will present this work at a conference like this. The first experimental measurement of Brillouin scattering is directly linked to the Raman effect. This is a guy Gross, so in 1830, he tried to measure Raman effect in different media. But the frequency shift doesn't correspond to Raman effect. It corresponds to Brillouin effect. So you can also find this paper if you are interested. It's a very short paper. It's just one page, one or two page. And you see here, this equation was given by Brillouin. So he find so very good agreement, not very good, but quite nice, between shift in different liquid and calculation. So in optical fiber, we compare every time, so I don't know why, we compare Raman and Brillouin scattering. That's it. So I have different explanations. So in silica, you have two distinct vibrational mode. So one is Raman scattering and the other one is Brillouin scattering. So Raman scattering, it's more like optical light vibration. Okay, so it's a really high energy phonon with low momentum. It's a really large frequency shift, and this frequency shift only depends on the materials. So it's a non-strict phase matching. If you inject green laser or telecom wavelengths or telecom laser, the Raman shift is always 12 terahertz in silica. It's different in Brillouin scattering. It's a collective vibration, so it's an acoustic live vibration with low energy phonon, high momentum. It's a small frequency shift. It's only 11 gigahertz. So it's really difficult to see sometimes Brillouin scattering because the frequency between the pump and the backscattering signal is really small, really close to the pump. And this is a very strict phase matching condition. So this frequency depends on the pump wavelength. If you inject green laser, the frequency silica is around 30 gigahertz. So in silica fiber, so go to the energy conservation and the momentum, it's really easy because it exists only two directions. This direction and this opposite direction. Due to the very long interaction, we have no theta is equal to p. It's impossible to have another point. Just another point is theta equal to 0, but I just explain you after. So the Brillouin shift, it's only this relation, 2 times refractive index, acoustic velocity in the media defined by the pump wavelength. That's it. So it's easy. And this is the phase matching condition. The pump, the backscattering signal, and the acoustic wave. So in single mode fiber, in backscattering configuration, we only excite compression wave, like this. So inject a light, you create compression wave from noise or depends or from different interaction, and you have backscattering light in this direction. So this is really backscattering Brillouin. And another point, it's forward Brillouin scattering. It's when acoustic wave vector equal to 0, not exactly equal to 0, close to 0. And in this case, this is not a compression elastic wave, this is a more shear wave. But it's not really efficient in single mode fiber, because in silica rod, like this, it exists two different family of acoustic mode. One is torsion radial mode, like this. So this mode modifies the polarization of the light, and another one is radial mode. And radial mode induce phase modulation along the fiber. This is a really low frequency shift, very close to the pump, and in silica fiber it's equivalent to a noise. It's not really important. It's more important in photonic crystal fibers. I will show you after. So, okay, first I will present you some effect of Brillouin scattering in standard single mode fibers. So I really like this this diagram coming from my colleague Luc Thévenin in EPFL. So if you inject a pump wave and signal wave in counter propagation in a fiber, with the frequency shift correspond to the Brillouin resonance in the fiber, you create, of course, interference, so a bit density signal, and by electrostriction, you create an acoustic wave, and elasto-optic effect, you can create a refractive index rating moving at the velocity of sound in the silica, and this refractive index, by diffraction, you have an energy transfer between the pump to the signal. So you can reinforce this interference. So if you increase the pump power, you reinforce this phenomenon. So the signal wave come from laser, for example, but it's possible to start from noise. It's not necessary to inject a signal. Okay? So in frequency domain, this is like this. So this is a frequency. This is a pump here in red. This is here the probe. So here the shift corresponds to the Brillouin resonance in the fiber, so around 11 gigahertz. So you have energy transfer here. So we create a dip here, and we transfer energy to the probe. So the LAN width, it's around 30 megahertz. It's directly related to the phonon lifetime in silica. It's a Lorentzian shape. And that's it. So Brillouin scattering in optical fiber. This is the first paper, stimulated Brillouin scattering in optical fiber by Ippen and Stollen from Bell Labs in 1972. So the same here as a fiber with a loss 20 dB per kilometers. So really simple experiment. So just a fiber, I think 5.76 meters. So inject a light, so it's a green laser, it's a CW green laser, inject with lens, it detect here, so inject this pulses, so it's a pulse, it's not CW. You observe a transmission, so this is here, this pulse here, and here you observe the backscattering with a Fabry-Perot étalon, and you observe this this pulse at the Brillouin resonance. So it's the first Brillouin measurement in optical fiber. What is the most important in this paper? This is the last sentence, experimental result, and the implied limitation to optical fiber transmission. Because the same here, Smith demonstrate that the Brillouin scattering and Raman scattering limit the power handling in optical fibers. And this is the real problem for telecommunication. So Brillouin scattering plus optical fiber, it's a problem. It's a problem for data transmission. So you see here, for a fiber with 20 dB per kilometer attenuation, the maximum transmitted power, it's only 35 milliwatt. So it's really low. So we discuss now how it's possible to have this very low pump power. So to define the Brillouin scattering process, we use three covariant coupled equations detailed by Robert Boyd in this paper and in the book also, Nonlinear Optics. So one equation for pump, one equation for signal, and one equation for acoustic wave. It's simple model, but it works. So you have pump, amplitude, frequency, also for acoustic. Frequency, so the frequency of acoustic waves is the difference between pump and signal, and backscattering signal. So in frequency, you have a Lorentzian shape, and the lifetime is directly related to the line width of the Brillouin spectrum. So in steady state situation, we can reduce the three equations to two equations. So one for pump, one for signal, and now you have the Brillouin spectrum, the Brillouin gain with different parameters, so refractive index, photoelastic coefficient, P12, velocity of light, pump wavelength, density, acoustic density, acoustic velocity, and the Brillouin line width. So this is the Brillouin line width measurement in silica fibers. And if you imagine now a very long fiber, you inject a light, okay, just a light. So we have a small part of transmission light, and we have some backscattering light. And if you increase the power, the difference between the signal at the end and signal here at the start is defined by this equation, depends on the Brillouin gain, the pump power, effective area, and the effective length. And it's voilà, just an example. So you inject a light, a transmission. So just to start, you observe just a backscattering light is from a Rayleigh scattering. Okay, so it's a linear case. But if you increase here, you saturate the transmitted power, and you arrive at the name is Brillouin threshold. Is when 1% of the injected light is reflected. And if you increase the input power, all the light is reflected. So we define this threshold, depends on the effective area of the fiber, the Brillouin gain is the effective length. So Brillouin scattering limits the power handling capacity. So in a modern single mode fiber, so 100 meter, the maximum power is 1 watt. So it's a really huge problem for high power fiber laser. And for very long single mode fiber, for example for telecommunication, the maximum power is 5 milliwatt. Maybe this pointer it's 5 milliwatt. So it's a really huge problem. So many people, since 40 years, working to reduce Brillouin scattering in optical fibers. So it's a really huge activity. So I just show you some idea to reduce Brillouin scattering. So you have in frequency domain the pump, the Stokes, so energy transfer. So how to reduce this energy transfer? The idea is just to transfer energy at different frequency. Okay. So in this case, you have not only one Lorentzian shade, but a very broadening spectrum. So how to do that? The idea is just to change the velocity of light along the fiber. Okay, so just change the temperature of the strain along the fiber. So of course you create different frequency, different Brillouin frequency, and you can broadening the spectrum. Another idea is to change the materials. Because standard single mode fiber is a doped core, you can maybe put some phosphor, fluor, change the acoustic profile, optical profile. Another idea is to taper the fiber or to change the effective area of the fiber. So it exists many configurations. I just show you different solutions. One is to apply the strain profile along the fiber. So it's a different system. So you have here it's a work pattern by Onera a few years ago. So in black, this is the Brillouin spectrum in fiber without strain, and in red, this is the Brillouin spectrum in when the strain is applied. So Brillouin spectrum increased to 3 dB. So it's correct. It's nice. this solution is really nice because the linear losses doesn't increase. Because in different cases, you can increase the Brillouin threshold and also increase the losses. Another one is to use different materials. So here this is a very standard Brillouin spectrum. I need different materials based on aluminium, germanium. We can increase the threshold to 6 dB. Another work here is to use aluminium fiber, and for different concentration it's possible to increase the threshold to 20 dB. That's nice, very good. But for this concentration, the linear losses, it's around 200 dB per kilometer. So this solution is only valid for small lengths of the fiber, especially for high power fiber laser. Another solution, really nice for from data from optical telecommunication. So you have a very long fiber, amplified signal. So to reduce this, it's possible to put isolator at different position along the fiber, because the isolator, the light go only on this direction. Okay, so this light coming from here, it just stop by an absorption. So 5 kilometers of fiber is just a sum of 5 times 1 kilometers. So this solution is used in telecommunication. Another one, I don't know if it's a reality or just a publicity. It's a company from USA. He uses a fiber with a special coating. The idea is to put some liquid nitrogen at high pressure to overcome Raman scattering and Brillouin scattering. Because Brillouin and Raman scattering come from thermal noise. So if you go to 0K, you have no Raman scattering and no Brillouin scattering. So the idea is to put some liquid nitrogen to reduce the temperature of the fiber. But I never see this system. I don't know if it's just an idea or reality. So now I will focus on distributed Brillouin fiber sensing. So we see that Brillouin scattering is a problem for telecommunication, but Brillouin scattering can be very useful for fiber sensing. So the first paper published where the Brillouin scattering can be interesting for fiber, it's an optical fiber attenuation investigation using Brillouin scattering between a pulse and a continuous wave. So the pulse is a pump and the continuous wave is a signal. So this is the system. So you see the laser here, so at telecommunication wavelengths, the fiber, the detector, and here this is the signal. Okay, and he measures locally the losses along the fiber. So here this is the trace of oscilloscope, and these 2 micrometers count, it's equivalent to 200 meter spatial resolution. So he mapped the losses all along the fiber. After that, different people working on different chain to create very famous Brillouin sensing. It's a Brillouin optical time domain analyzer. So this is 2 paper where he measures the distributed strain in optical fiber. So you see it's 2 kilometers. He applied different strain. So this is a dot here profile, and we observe the Brillouin shift, and you can see the strain applied locally at different positions along the fiber. Also for temperature here, so in a piece of fiber, you put on a thermal bath to increase the temperature, and you can detect locally the variation of the temperature. So by using a pump probe measurement in very long fiber, it's possible to map the temperature and the strain variation all along the fibers. So this is a main shame. So we use a DFB laser. Why we use DFB laser? Because because the line width is around 100 kilohertz. So this is a very coherent laser. We split into 2 parts. The first part here, it's a pump. So we just modulate, just amplify or modulate to create a pump pulse. The duration of pump pulse defines the spatial resolution. Okay, so we inject here in the very long fiber, and in this second arm, we use an electro-optical modulator to generate two sidebands shifted to the pump here at Brillouin frequency, at the Stokes Brillouin frequency and anti-Stokes Brillouin frequency, and we inject in the fiber. And at the end, so if the shift here corresponds to the Brillouin shift, you have an energy transfer between the pump to the signal. Here, with this system, we select Stokes or anti-Stokes line. Okay, so Stokes is the gain and anti-Stokes is absorption, and we observe an oscilloscope, the amplified signal. Okay, so we synchronize here this pulse time here, SOA and oscilloscope, and we obtain this map. So to obtain this map, we just change here the frequency. So for each frequency, so 10.5 to 10.9 with a step of 1 megahertz, we record the trace on oscilloscope. So the trace in time, it's equivalent to a trace in distance, okay? If you know the speed of light. So you have here along the fiber very homogeneous fiber, so at 10.7 gigahertz, and two sections here. One it's heating, so we have a Brillouin shift, and here we apply some strain. So it's a very useful technique to detect variation of temperature. So here you see the Brillouin sensibility as a function of temperature. So we can detect 1 megahertz per degree. So it's nice. So you see here the variation. You can remark also that the amplitude change. Okay, when you increase the temperature, you increase the number of phonons. Okay, so we increase the amplitude and increase the shift. And also when you apply the deformation, so here 0%, 0.3, 0.5, you also see a Brillouin shift, and here the amplitude decrease because we increase the length of the fiber. And this is the deformation. So in standard single mode fibers, the maximum deformation is around 1% before break. So that's it. And you see one difficulties is that the deformation and the temperature variation have the same variation. So when you apply deformation, you increase the Brillouin shift. When you apply the temperature, you increase the Brillouin shift. So you don't know exactly when you see a defect here, you don't know if it's an effect of temperature or an effect of strain. So many group working on that to differentiate temperature and strain effect. So distributed Brillouin sensing. So I will show you different parameters in different materials. So in this configuration, the effective index and also the acoustic velocity depend on the strain and the temperature. And you see here different, so this is a silica single mode fibers. So you see the variation as a function of strain and temperature. It's for telecommunication wavelengths. It's telluride, chalcogenide, germanium doped, etc. So we try to find plus here and minus here, but it's quite impossible. It's you have plus for strain, you have plus for temperature, etc. So this is a big difficulty. But we can apply this distributed measurement in different configuration. So today, 10 industry, 10 company working with Brillouin scattering in the world. So mainly for oil and gas distribution, of course. But now new application for energy here. So this company in Switzerland fabricate different Brillouin sensor. So with Brillouin sensor, you can detect variation of 1 degree with a resolution of 1 meter over 75 kilometers. So it's a nice system. So I will show you just a specific point of distributed measurement. So this is interaction. So you have a weak signal, the fiber, you create an acoustic wave, and here the pump, so it's an intensity pulse, and the frequency between the pump and the signal correspond to the acoustic resonance of the fiber. Okay, so you have energy transfer, it's perfect, classic. But now you want to increase the spatial resolution, because 1 meter, it's okay from some application within maybe shorter, 10 centimeter, 1 centimeter. So to do that, you reduce the pump pulse. Okay, but if you reduce the pump pulse, you increase the pump LAN width, and the signal here, the bandwidth is given by the convolution between the pump spectrum and the Brillouin spectrum. So if you use pump pulse smaller than the acoustic lifetime in the materials, you have a very broadening spectrum, and it's impossible to detect variation of temperature or strain. So this is the main limitation, and during many years I working on that, to how to reduce spatial resolution and increase the sensibility in Brillouin scattering system. So the idea is to use a P phase shift, not intensity pulse, but a P phase shift, because in this case it's a 2 CW wave. Okay, so we have no broadening, and we can probably detect variation smaller than the acoustic lifetime in the materials. So how to realize experiment? So this was a collaboration with EPFL, with the group of Luc Thévenin in Lausanne. So we use again the same laser, the 2-arm, but in this part we didn't use intensity modulator, but just a phase modulator. That's it. Okay. So phase modulator, we use a very short pulse. Here again, electro-optical modulator to create 2 sideband, sensing fiber. So we inject and we detect here Stokes or anti-Stokes in oscilloscope. So what we obtain here, we use 2 different fibers, because it's difficult to put a small part of the fiber in a bath to control the temperature, etc. It's too long. So basically we use 2 different fibers with 2 different Brillouin frequency shift. It's more easy for experiments. So one fiber, it's fiber 1 with a frequency of 10.86 GHz, and fiber 2 is inverse, sorry, is 10.72 GHz. So here we use 10 meter spatial resolution, 1 meter test fiber, and we detect, clearly we detect, so we have a spatial resolution smaller than the acoustic lifetime, and we can detect this small part of the fiber. We can also decrease the length of the test fiber, so 20 centimeter, we detect again, it's really low, but we detect, it's not a problem. So now if we observe in frequency domain and in type domain, so here, so this line here, it's in time domain, so this is what we obtain in oscilloscope. Okay, so we obtain this shape, and this shape is directly related to the phase modulation. So we have here an exponential gain and here exponential decay. So this is the signature of Brillouin scattering. And here in a spectral domain, we have here at this point, this is a blue line. So we have 2 peaks, okay? So this is here the unwanted signal. So this is the rest of the interaction of this 5 fiber. And here we have this point. So this is a problem for sensing community because here, normally we detect only 1 point. This point normally disappear. We have no interaction here. We have only interaction here. So we're working on different solutions to increase the signal to noise ratio. So one, it's a software solution. So to find how it's possible to manipulate this equation to increase the signal to noise ratio. And another one is hardware. The idea is to use 2 pulses. So one pulse is P, it's just a very long intensity pulse, and here pulse E, it's intensity pulse plus a P phase shift at the end. I will explain why. So how we create this. So it's a really fiber system. So here we use a first electro-optical modulator to create a very long pulse. Here the phase modulator, we create a P phase pulse. Here we synchronize to put the P phase pulse at the end of the very long intensity pulse. We have some polarizer scrambler. Scrambler is to scramble the polarization because Brillouin scattering is really sensitive to polarization. And we amplified and we obtain this measurement. So this is the gray line. So this is typically what we obtain in oscilloscope. Okay, so we take two trays, one for pulse A, so without phase modulation, just intensity modulation. So this is a blue line, okay, very long fiber. And in gray, this is a intensity pulse plus the P phase shift at the end. So now if you realize here A minus B, you obtain this trace, and it's our signal. So here the signal to noise ratio is larger than trace A and trace B. And it works. This is a basic measurement, so only with P phase pulse. You see here some exponential decay here, so this part is a problem. And now with two pulses, so this one minus this one, we obtain the same, of course, but here we have no signal. Okay, so it's really nice. We call then second echo. I will explain why later. So this is really nice. The problem, most difficult problem, is to realize this operation because we need two trays for each frequency shift. So it's a really long measurement. It's around 1 hour measurement. So if you have a variation during the measurement, temperature, strain, it's impossible to detect. So just to show you an example, so it's a very long measurement, it's a record. So for 5 kilometers, we have a spatial resolution of 5 centimeters, so it's equivalent to 100,000 physical points. So this is a total trace here, and when you zoom at the end, you find this part. This is a small section where you just increase the temperature. So it works very well. So we also working on a software idea. So we use again the same equation. I will go maybe a bit faster. So just initial condition directly related to the sensing measurement. So we have here the fiber, so with a finite length. Here this is a pump. We consider all configuration. This is why we use alpha, beta, and gamma. We can use intensity pulse, P phase pulse, as we want. And on a signal, we consider a very low amplification gain. Okay, so we have a CW signal plus a small gain. This part is important. Okay, so now this equation we can reduce to two equations because we consider no linear losses during interaction and no pump depletion. So only one equation for signal and one for acoustic wave. Now we can reduce to these two equations, and acoustic wave can be write like this, okay? And to see how acoustic wave is created, so we inject CW light, you create an acoustic wave, so just you see here this exponential, so we create an acoustic wave slowly, and here we apply the P phase shift. So the acoustic wave try to adapt to the new phase matching condition. But just after, we go back to phi equal to 0. So again, the acoustic wave try to adapt at the new phase condition. So acoustic wave takes some time because it's a mechanical wave. So we call then, we call this the first echo, and here the second echo. This is why we call this technique Brillouin echo distributed sensing. So in equation, this is the equation of acoustic wave. This is the equation for the pump. Okay, so we just use Laplace transform, and we obtain impulse response for different coding condition. So this is why it's important. This is an analytical solution, so it's not numeric or something like that. And we can define all part of the interaction. Before interaction can be interaction and interesting, during interaction and after. And we can separate the different parameter. So what is interesting, so it's not really interesting. This one is probably more interesting. We can simulate all coding case, because in distributed Brillouin fiber sensing it exists many configuration. So if this is intensity pulse, this is intensity plus CW component. So in this case, the idea is to pre-activate the acoustic wave before interaction. Here this is, we call then the dark pulse. So here we have no light during a short pulse. Here it's a p-phase pulse. So we can define and we can simulate all configuration. And you see that the most efficient is this one. You see the amplitude, 6 to -6, and this one 0 to 2. It's really different. So just different point. This is a classical BUTDA configuration, so intensity pulse. So we consider just one fiber, 1 meters of interaction with pump pulse duration 1 nanosecond. So you see this very broadening due to the very small pump pulse duration, very broadening spectrum. It's impossible to see some variation of the frequency here. So this is a response in time. And here this is a phase modulation. So just replace in experiment intensity modulator by a phase modulator. And this is the same price. And you have a better resolution. So here you have a Brillouin echo distributed sensing spectrum, and we have a very clear line. So we have the first echo and the second echo. So, but this one, it's not. It's like a ghost. We didn't want this this interaction, this signal here. So this is different configuration, not really important. I think for you, yeah. Just resume here. This is a spectrum. So for intensity case, so you see broadening and very low, dark pulse, and p-phase pulse. So the p-phase pulse, it's a more efficient. So if you back to experiment, this is a Brillouin echo distributed sensing with two different, with this case, so 2 fibers, one 10 meters, another one I think it's 1 meter, so this is the experimental result. And this is the analytical solution. So it's really nice. We clearly see, so okay, in analytical solution, the frequency here of the different fiber is homogeneous. You see here some oscillation. It's an effect of polarization. That's it. But we have a very good agreement between experiment result and analytical solution. Also, maybe, I don't know if you see some oscillation here and here. So it's really nice. And the idea is to use analytical solution to improve, again, the experimental result. Because here you see we have signal here, but we have no interaction. It's just the second echo of this fiber. And the signal is here. So the idea, so this is a trace here in time. So you see we have some interaction here, no fiber, so normally it's down here to 0. And you see in frequency, the ghost signal is larger than the real signal. So it's a problem. So the idea is the signal at the end, it's a convolution between the real data and the impulse response of the system. So it's really basic data processing. So the idea is just to use analytical solution for the impulse response to deconvolute the experimental result. And it's really fast because it's an analytical solution. So you see here the experimental result, and it's equivalent to a filter by impulse response, and you see here the signal is larger. We can zoom on different parts. So the blue is before data processing, the green is after data processing, and again here, so you see here, okay, we have also a small noise, but we really reduce this resonance, and this one stay the same. So we have suppressed all unwanted contribution to the signal. So this is really nice. This is a blue, this is the first measurement, because in fiber sensing industry, we just detect the maximum of the signal as a function of the position. So here we clearly see the small section of the fiber. So to conclude about Brillouin scattering in optical fiber, it's a love-hate relationship. As you see, Brillouin scattering limits the power handling capacity. You can see 100 meter, 1 watt. That's it. But it's possible to reduce Brillouin scattering by apply strain, by change the material, design acoustic properties, taper fiber as you want. But Brillouin scattering can be very, very interesting to create distributed Brillouin fiber sensing for strain and temperature. So this is typical performance of industry system, not in a research lab. And I will show you we experimentally obtain a distributed fiber sensing with spatial resolution of 5 centimeters. So now the limitation is 2 millimeters because we increase the detector, but it's more complicated, but this is the same idea. And we have shown how it's possible to use analytical time domain solution to improve the data measurement. So do you have questions about this part? Because now we'll move to photonic crystal fibers. No? Maybe at the end. Okay, so now I will present you Brillouin scattering photonic crystal fibers. So, and especially forward Brillouin scattering. So this is a macroscopic image of standard single mode fiber. So core diameter 8.2, you see maybe the core here. So doped core here, germanium doped core, effective area around 80 micrometer square at telecom wavelengths. And this is a different profile of photonic crystal fibers. So from different group, from different industries. So you see here. So it exists many design as you want, different row, different core, etc. This one is really interesting because it's not the same propagation as the one you see here. It's a hollow core fiber. So the light is guiding here. So here it's a hole, it's a hair. Okay, so the light is guiding by a reflection. It's a black reflection here. So it's really interesting. And this one also. So why using photonic crystal fiber for optics? One is to enhance nonlinear phenomenon, to manage dispersion, etc., to create, for example, super continuum. It's a very broadband sources. Another one is to use, for example, gas liquid or gas light interaction. So we can use this fiber or maybe this one, put some gas at different pressure, and if you splice with standard fiber, you have a very long gas cell, and you can use for reference laser, for spatial application, etc., etc. But what about photon and phonon interaction? So Brillouin backscattering configuration, so with compression wave, but in forward scattering, photonic crystal fiber is really interesting because you see the hair hole macrostructure can really change the interaction between optical wave and radial and torsor-radial mode. You see here this structure. So this is a forward Brillouin scattering. This is the idea. Inject a light. We have some acoustic wave, it's just representation, and we have some intensity phase modulation. So what is GOBS? GOBS is discovered by Shelby. Shelby want to realize quantum transmission with fiber and is limited by this phenomenon. So GOBS originate from thermally excited fluctuation in the refractive index of the fiber. So the most important is the polarized GOBS caused by pure phase modulation noise. And in photonic crystal fiber, microstructure modifies the acoustic mode at different frequencies. So if you inject a light, okay, you have different shear acoustic modes, so phase modulation here and polarization modulation. In standard fiber, this is the interface between silica cladding and the protection, which create this acoustic resonance. So, and here this is a phase matching condition. So how to observe this effect of acoustic mode in a propagation light? We use this phenomenon, this shame here. We call them nonlinear loop mirror. It's equivalent to a Sagnac interferometers. So we inject a light. The light is come from DFB laser, again with very low LAN width, thanks to the telecommunication. We amplify. It's a CW laser. We filter for the noise of amplifier, and we inject a light here. So we split in two parts, one part here, one part here. And the two arm receive the modulation, and at the end here, cross here, and this one move here. And when the light cross in this direction, the light receive a P phase shift. This is a configuration of the coupler. So in this configuration, the phase modulation is modified to intensity modulation. Sorry. So we can observe in an electrical domain. So it's a whole fiber system. So we use different fiber with different geometry. You see here different core diameters, 11, 4, 2.8, different ratio core diameter to pitch, the length, different lengths of the fiber, etc. So what we obtain, this is a Gaube spectrum in standard single mode fiber. So from frequency to 0, so 0 it's a pump frequency, to around 800 megahertz. The frequency is directly related to the diameter of the cladding. Okay, cladding here, 1.25 micrometers, not the difference between the core and the cladding. Okay, this is really the cladding here. Now in photonic crystal fiber, you see the Brillouin spectrum is different. So you see here in the large core, we have different resonances, but stop at 400 megahertz. And here for two small photonic crystal fiber, we have one resonances here, as depends of the structure. So with a good quality factor. And it exists a really strong isolated acoustic phonon in the two photonic crystal fiber core with the smallest core here. And the hair hole microstructure plays the role of a filter for a different acoustic wave. Okay, so here this is a shear wave, mostly shear wave. So if you can some simulation, very simple simulation, we just simulate the optical propagation in this photonic crystal fiber. You simulate here is not really clear, but it's elastic on energy of the acoustic mode localized in the core of photonic crystal fiber. It's a finite element solver. We can make just an elasto-optic coefficient, so it's just an overlap, okay, between two optical mode and elastic part. And we can obtain here different points. So the cross is the experimental point. So this is a frequency as a function of core diameter, and we see this is a resonant acoustic resonant phonon. We have a produce here, so acoustic velocity multiplied by the core diameter is around 3.2 kilometer per second. Okay, so we have a good agreement between experiment and numerical result. Just to show you just another experiment, so we have different resonances. Each family here is related to the different row of the photonic crystal fibers. Okay, so this is some calculation, not so perfect, but you see here this point. So this is these resonances here. We not see clearly, but here this is linked to the second row, and here for the third row, etc. So we try to use this technique to find the homogeneity of the photonic crystal fiber along the fiber, but it doesn't work. Another application, it's again for Brillouin, it's sensing, okay? So, but it's not really sensitive. Just the sensitivity is linked to the materials, not to the microstructure. Yes?
May I just quickly ask to recalibrate? We are now talking about forward
Yes.
scattering
For
from
what?
shear waves,
Yes.
and before it was backward scattering
Scattering.
from longitudinal waves.
Yes.
And I think in the first part of your talk you quickly said that the shear wave scattering is not so important, or so I think you said something like this.
Yes.
So
In
why is it now important?
is now important because we have a microstructure. Uh,
But it didn't look so different when you compared it to the standard fiber, so that's why I was asking this.
yeah, I understand. For standard five fibers, you have like this. You have up. I just it's a scale. Okay. So here it's 125 micrometers. Okay, and the core here it's 10. It's around 8 micrometers. So the light propagate like this. Okay, but the acoustic, the shear wave evolve here. So in this region, so the overlap between shear wave and optical wave is really low. The interaction is really low. But in photonic crystal fibers, you have the same, but this structure here, you have the optical wave here and also the acoustic wave in the same region. So the overlap is really huge. So we can detect more easily. That's it. It's just this point. You understand?
On the very beginning slide of the gauges,
Yes.
it didn't look so much different.
This
The
one?
left and the
Oh,
so
no.
I don't know. Yeah, this
Yeah,
one.
yeah.
Exactly the one that you were.
This one?
Yeah, if you show the two spectra,
Yeah.
I don't see why they are so. What is so different?
This one is for 1 kilometers. Okay. This one is for 10 meters. This one for 5, and this one I think for 10 meters. The difference is it's a length.
Okay.
Okay, I didn't specific. Yeah,
Maybe
yeah.
sorry.
And the frequency here, it's really the Bessel function related to the this diameter, and the light propagate just this, so the overlap is really low. It's a problem for quantum, etc., but not for telecommunication, for example. Up. Another question? Maybe when I tuk. So another application or interesting, it's possible to enhance the acoustic phonon localized as a really specific frequency. So this work was realized by the group of Philip Russell in Erlangen. So he used a very small core photonic crystal fiber. The core is around 800 nanometers. So really confine the optical wave and the acoustic wave. This is why the frequency is really high. And he tried to increase the phonon interaction. Another point, he used polarization effect of the torsor-radial mode to realize an all-optical attenuator. Inject a light like this, and the acoustic phonon transfers the energy in the opposite axis, and it's possible to create optical attenuator. But it's a little bit difficult. So this is why forward Brillouin scattering it's a bit interesting for in photonic crystal fibers. So now I will move to another point. It's backscattering configuration in photonic crystal fibers. So this is why I use this this representation. So this is really a compression acoustic wave. So when photonic crystal fibers appear, many people, many groups, okay, I want a photonic crystal fiber and I would like to realize a Brillouin measurement. Okay, so different groups. So here, I think it's the first paper. So the first photonic crystal fiber is 1997 from the group in Southampton. So this is the first paper, and it's a bit interesting because we have many resonances, and the variation of the frequency as a function of temperature or strain is not the same coefficient. So many people say, okay, it's maybe possible to discriminate the effect of temperature and strain. Okay, why not? Another result, sorry. It's a result presented by a group again by Philip Russell. he measures the Brillouin threshold in different photonic crystal fiber when the core of photonic crystal fiber decrease. And he observed that the Brillouin threshold increase. So it's quite really interesting because you can confine optical wave and you can probably reduce the Brillouin scattering effect. So this is a Brillouin scattering in a large core. This is a Brillouin spectrum in a small core, so this fiber. So we see different resonances, and this is a acoustic, this is a compression wave, this is a simulation compression wave along this small core photonic crystal fibers. But the problem in photonic crystal fiber is that Brillouin spectrum is different. So when you have a photonic crystal fiber, you measure the Brillouin spectrum and you always obtain a different result. So it's really difficult to progress. So this is a result obtained in my group. So this is very basic single mode fiber, very nice, low enchant. Here 2 peaks, here 1 broadening peaks, another one 3, here many peaks. So it's really, really difficult. So here the idea with my colleague Vincent Laude is it possible to write a new model to explain this phenomenon? So just summarize a little bit. So in backward configuration, so in this case, we have different resonances. So it's one of few resonance, mostly longitudinal phonon, but we don't know exactly it's only longitudinal. The frequency is around 11 gigahertz. In forward configuration, this is in single mode fiber. Here in photonic crystal fiber, again with different resonances. And we have several resonances, and the frequency is around 11 gigahertz. So we wish to model electrorestriction of phonon wave packet in arbitrary waveguide or fiber. And it's really interesting because when we make some result, we observe with my colleague Vincent that for Brillouin backscattering interaction we use one model, so it's a free coherent coupled equation, and for Gauss configuration we use another model. It's strange because we just change the acoustic wave vector. So normally we can use the same model but just change the initial condition. Mainly because this model from Boyd use acoustic from fluid, and in fluid it doesn't exist shear wave. And he used also plane wave hypothesis. So we decide to working on a new model, mostly on my colleague Vincent because I'm more experimented. So we use this equation. So we call then elastodynamic equation as a function of acoustic pulsation and acoustic wave vector. So we have here the three components of the displacement, the mass density, the elastic constant tensor here, the deformation, and also an optical stress tensor. This is really new because basically we use this equation but equal to 0, and we try to find the eigenvalue solution. But here the idea is really to use optical forces to detect really which acoustic mode are generated. So this is here the definition. So you have the photoelastic tensor and the two optical waves, so the pump and the signal. So to introduce phonon damping, we use a viscoelastic tensor. So it's just an imaginary part of the elastic constant, and we use QF product, so it's a quality factor multiplied by the frequency. It's a constant, so in silica this is this value. So we assume two optical waves, okay? So one for pump, one for signal, and guided acoustic wave. We also define the phase matching condition, so we just find as a function of backscattering configuration or forward scattering configuration, and we can compute different solutions, but we compute the kinetic energy of the elastic wave as a function of the frequency. So just some example. So this is a silica rod. So here 1 micrometer, 1.5 micrometer. So this is a optical calculation here. So you see the evanescent field here. It's air. Okay. This is the optical forces. So this term here. So the optical stress tensor is represented here. Okay, so it's only defined where we are materials. Okay, in here we didn't define optical forces, and you calculate. So in red, this is a previous equation equal to 0. So this is the eigenvalue solution. So we find many solutions, but we don't know exactly if it's guiding or not. And this is for Gauss configuration. So here in this is so black line. This is a calculation. So we see which resonance is activated, and this is for backward configuration. Of course, we have more acoustic resonance because we move to the diagram dispersion. Another test, it's a silica rod, a silicon, so with different photoelastic coefficient. We test different configuration, and we also find where we have a peak in our calculation, we find an eigenvalue solution. So it's a good point. Another result, basically, we use this. This is, sorry, this is in French. This is a diagram dispersion, so elastic diagram dispersion, so the frequency, normalize acoustic wave vector, etc. Okay. But for us, it's too difficult because Brillouin scattering is around here, so many elastic resonance, and it's just for silica rod of 1 micrometer. Imagine for photonic crystal fiber with a core of 10 micrometer, it's completely black. And here, this is our calculation. So we see clearly the elastic branch excited by optical forces. Okay, and the black line, this is a basic phase matching condition. So we had quite good agreement. So now in photonic crystal fiber, this is our objective. So we just use a macroscopic image. We mesh. Okay, we use. I use COMSOL, and my colleague Vincent use FreeFEM. It's a free software, interesting but difficult. This is the optical power density. This is the electrostation stress in Pascal. So, and we solve for, okay, it's just some initial conditions. So of course, at telecommunication wavelengths, we normalize for 1 watt incident optical power. And okay, two solver, COMSOL, and this one, if you want to manipulate a finite element method in a free, with a free software, we can use this one. So in standard single mode fibers, this is the experiment. So Gauss, so forward case, backward case. This is also calculation. So we have a good agreement. We observe again single resonance in backward configuration, different resonance in Gauss configuration. In our calculation, we just change the phase matching condition and the frequency window. Okay. So for each frequency, we calculate the elastic energy, and after we map this spectrum. And we can also map different properties of elastic waves. So here, this is elastic energy of these resonances, where we see this is a core here, and this is a cladding. So we see that the elastic resonance fill completely the fiber. And here, at this frequency, the elastic resonance is really confined in the core of optical fibers. So we also applied in photonic crystal fiber. So more beautiful picture because we have some hole, but this is the same case. We see clearly the effect of the microstructure on shear wave here. So here I think this is elastic energy and kinetic energy, and here this is the transverse displacement. So we see here this point, this resonances is really confined in the core of this photonic crystal fiber. And again here, these resonances at 11 gigahertz is really confined in the core of photonic crystal fiber. So when we realize this calculation, we find a very nice result. Here I just plot the the X position. So this is the optical power here in this single mode fiber, and here the optical power in this photonic crystal fiber. So the core of this fiber is 8 micrometer, and the core of this photonic crystal fiber is 11 micrometer. So it's quite close. Now we add elastic energy for Gauss configuration. So you see in single mode 5 fiber, this elastic energy fill completely the fiber. Here also for photonic crystal fiber we see the decay due to the hair hole microstructure. And now this is the elastic energy in the backward configuration. And you see what is interesting? Elastic energy is more confined than the optical energy. You see here the red for single mode fiber and the red for photonic crystal fiber. So in this case, the phonon wave packet is contained within the electrostation stress distribution. So the idea is just the guiding effect is not provided by the microstructure here, but it's equivalent to a gain guidance in semiconductor laser. So it's really simple, but the acoustic phonon exists where the light propagates. For community of in optical fibers and Brillouin scattering is not evident. Okay, but here it's a clear demonstration. So just short result to show you that this model really works in different configuration. This is the experiment in one photonic crystal fiber, Gauss configuration, backward configuration, and also this is a simulation. So now we have a very powerful tools to calculate the Brillouin spectrum in different configuration in all materials, all configuration. It's not restricted to silica fiber. We test in liquid, in gas, in many configuration. When you have just light is guide, we can calculate the Brillouin spectrum. So in this case, the longitudinal deformation, so here, is dominated by the total deformation and is confined by the combination of hair hole microstructure and the optical forces. So if the core is really small, you have a competition between hair hole guiding effect and also the optical guiding effect. So we applied this model at different area, and one it's work with FLAM in Lille. FLAM it's a lab and fabricated different photonic crystal fiber, and the idea is again to suppress Brillouin scattering. So the idea is to taper a very long photonic crystal fiber to create a very broadening spectrum. So this is here the picture of photonic crystal fiber. It's a PM fiber, so polarization maintaining fiber. This is the external diameter here, okay. The total losses is around 30 dB, and this is here the refractive index, so the blue and the black, and the red, this is the birefringence. So it's nice, 10 point -3. For fiber, it's nice. And you see here the Brillouin shift as a function of effective index, acoustic velocity, etc. So from this calculation, the Brillouin spectrum can be broader to 1 gigahertz. So in experiment, we just use a very simple experiment. The fiber is here, the laser is here, so it's a CW current laser. We amplify here, so the light here, and we just observe the backscattering light, the bit between backscattering light and the small part of the pump in electrical domain. It's a heterodyne detection, okay? So it's like spontaneous measurement. We inject a light and we just observe the backscattering light in electrical domain, because in electrical domain we have a very high spectral resolution. So we have different sample, one homogeneous sample, one tapered sample. So this is the result for the two polarization axis in this homogeneous section. So we have a classic Brillouin spectrum in photonic crystal fiber, little bit broadening. And when we measure the Brillouin spectrum in this tapered fiber, we observe a broadening, but not very huge. It's not 100 gigahertz. we have a little bit broadening here, but after it decrease, okay, normally it's more like square. The problem is this resonances coming from the N receive many optical losses. So it's a problem, but also the Brillouin threshold increased to 6 dB. So we make some simulation, but it's difficult because it's a polarization 5 fiber, so it's not easy to simulate. So this is the experiment, and we calculate the Brillouin spectrum at different positions along the fiber to find where this resonance coming from. So you see here, this is a large section of the 5 fiber, and we decrease, but we didn't see this section, then we didn't see this interaction here, so we clearly see only this part, so probably the interaction starts here, and this is here just noise. So it's not, again, the perfect fiber to suppress Brillouin scattering. So another idea, very nice idea, we never publish this result, I don't know why. This is, okay, two different fibers, single mode fiber, photonic crystal fibers. Here, this is a distributed Brillouin spectrum along the fiber using high spatial resolution measurement. You see beds measurement. So with 30 megahertz, 30 centimeter spatial resolution. So here it's really clear. So it's 10 meters and it is longer, 100 meters. The idea is to measure the acoustic decay time in these different fibers, because with high spatial resolution system, we have spatial resolution lower than the acoustic lifetime in the material. So it was really nice because here, this decay is directly the signature of the acoustic decay time in the fibers. So if we plot this, so at the end of the fiber, normally the interaction stop here, but we have a small decay, just 1 minus exponential minus t over ta. Ta is acoustic lifetime. Just a small, here this is a spectrum, so we have both spectral measurement and time measurement, and it's directly related. We find here it's 12 nanoseconds at a frequency of 10.73 gigahertz. So it's a direct observation of the acoustic decay time, and in single mode fibers, a line width corresponds to the acoustic decay time. This is, I think, the only measurement of the acoustic decay time in silica fibers in this configuration. Because in photonic crystal fiber, many groups say, okay, it's probably broadening spectrum along the fiber because the hair hole is not really homogeneous along the fiber, is maybe effect of current, phonon, etc., etc. So the idea, okay, we'll measure the acoustic decay time at the end of photonic crystal fiber, and we'll see what is the origin of this broadening. Okay, so we have a very large broadening, 52 megahertz, and you see here the lifetime, it's 7.6 nanoseconds. So it's different to silica, but the fiber, it's a silica fibers. It's photonic silica fibers. So why? Why we observe a short decay time? It's not so difficult, it's just a superposition of different Lorentzian shape with a line width corresponding to the silica, okay? So here we just realize a 4 Lorentzian model with 4 different Lorentzian. So in red, this is the sum of 4 different Lorentzian here with different frequency, but the same line width corresponding to the silica. And here we use this processing to calculate the frequency evolution as a function of distance. So we just data processing this spectrum, okay, at each position. We use this model, and we find that all frequency move with the same evolution. So this is probably just a superposition of different Lorentzian shape. We don't know exactly why we have 3, 4, 5, 6 different Lorentzian shape in Lorentzian in a photonic crystal fiber, but it's a clear demonstration of superposition of different Lorentzian shape in photonic crystal fibers. That's it. Yes. So this is.
Did you perform experiment like this, changing the power?
Yes. Yes. No variation. We have here. This is for distributed measurement. We working on a linear regime. You remember when I brought the injection input power, and here the transmitted power, and you have this okay, and saturation, and backscattering is like this, okay, like this. Sorry. For distributed measurement, we always working here. We didn't working on here. It's more complicating. We have many reflection effects. It's not really noisy, really not stable. So we're working on linear regime. So for many person, Brillouin scattering is not nonlinear effect, because while we're working on this regime. So when we increase the power, if you really increase the power really high, the relation shape evolves to a Gaussian shape. Okay, if you have a Lorentzian like this, Lorentzian, you apply the exponential gain in in, uh, with a pump, you have again after a Gaussian shape with a narrow LAN width. So conclusion, so we have investigated a unified electrosensitive model of Brillouin scattering in micro nanostructured optical waveguides. So what is the next about this model? We want to add other forces like radiation pressure forces, thermal forces, etc. To see the effect on different cases. We progress on that. This model describes the experiment performed in a photonic crystal fiber. So it's valid for arbitrary cross-section, for arbitrary materials as you want. We give many information. We see that the guiding effect, the guiding, it's really, the phonon is really guiding by the electrosection stress distribution along the fiber. And it can be very interesting to understand the origin of Brillouin scattering in on optical forces in waveguides. So this is the end of photonic crystal fibers application. Do we have question? Maybe we can make a short pause, coffee, if you want, 5-10 minutes as you want. Okay, 10 minutes before the end of taper.